Hello everybody, my name is Harsha Nagarajan and I am a staff scientist in the theoretical division at Los Alamos National Laboratory. Today I will be presenting about QuantumCircuitOpt, an open source framework for Provably optimal quantum circuit design. The outline for this talk is as follows. I'll give a short introduction to quantum computing and a necessity for the package of this type. Then I'll present the underlying mathematical programs, followed by introduction of the package and its features. Then I'll be presenting a few compact circuit realizations obtained using the package and conclude the presentation. I will now present a quick background on quantum computing. As we know, computing is everywhere. Computation has played a major impact on the society in multiple areas such as science, engineering, entertainment, health, social media, to name a few. In particular, supercomputers for performing big numerical calculations can be very helpful. On the right is the Trinity supercomputer, which we have here at lanl. So there is a desire for computational speed in every computation we perform on a day-to-day basis. While certain simulations without actual experiments are very important, some problems are just way too hard to solve. A single program can take many months on a supercomputer. Although there have been tremendous improvements in achieving the desired computational speed, there are also limitations to classical computing. As it can be seen in the microprocessor trend data on the left, Moore's law states that the number of transistors in integrated circuit chips roughly doubles every 2 years. However, there is also a fundamental question which rises. While hitting such basic physical limits, what exists beyond Moore's law to solve computationally hard problems? The answer to this question is quantum computing, as suggested by the Schrodinger's cat. We all know that there has been a push towards useful quantum computing across United States by both Department of Energy and various industries. There has also been a race towards quantum supremacy from all around the world. One of the reasons for such a push towards useful quantum computing is the tremendous speedup it is able to provide for certain types of problems which are very hard on a classical computer. For example, for the prime factorization of an n-bit integer, Shor's quantum algorithm provides a super polynomial speedup in comparison with the fastest known classical algorithm. On another important class of an optimization problem called the semi-definite programming, quantum algorithm provides a polynomial which is a quadratic speedup over the fastest known classical algorithm. Many such algorithms can be found at this link where quantum computing has been found very effective and useful. A quantum circuit is a way to implement an algorithm on a quantum computer. In simplest terms, a quantum circuit is an ordered sequence of unitary gates performed on qubits, where a qubit is a quantum version of a bit. Usually, these unitaries are applied on 1 and 2 qubit gates, representing any arbitrary entangled state. A quantum circuit, as can be seen in this figure, takes in as an input a preparation of an initial pure state, performs matrix operations on them as an unitary evolution, and then as an output, measurements of observables are taken to obtain certain state vectors. A primary research goal by doing this is to be able to decompose a desired quantum algorithm, also known as a target gate, into a shortest possible sequence of 1 and 2 qubit gates. The reason any target quantum gate needs to be decomposed is to be able to map it into specific architectural constraints of the quantum processor's hardware. For example, a 2-qubit reverse CNOT gate on the left side of this figure can be equivalently implemented using 4 1-qubit Hadamard gates and 1 regular CNOT gate. Now let us look at a few popular hardware-based native gate sets. In the IBM's 5-qubit processor, while the native gate set includes these 3 gates, the Rigetti's 8-qubit processor includes these 3 gates as the native gates. As mentioned earlier, any quantum processor includes 1-qubit and 2-qubit gates as their native gates. So what we really care about is to reduce the measurement noise in a quantum processor. The key properties that define the quality of a transpiled circuit in a processor are as follows. The error rate of 1 and 2 qubit gates. Typically, the entangling 2 qubit gates like C0s are much more error prone. Also, the total depth of the circuit, where a shortest possible sequence provides a better quality of measurement, and also the interqubit connectivity and the qubit coherence times. In this work, we will be focusing on the first two properties, which is minimizing the number of error-prone 2 qubit or the C0 gates, and also the total depth of the circuit. While numerous off-the-shelf packages like IBM's Qiskit provide good quality circuits for implementing in a quantum processor, they do not really provide a mechanism to measure how close they are to the best possible circuit. So the community is lacking both methods and software packages that can provide theoretical guarantees on the solution quality of the obtained circuit decomposition. In this work, we will be presenting mathematical programming based methods which can provide provably optimal quantum circuit design. Let us now look at the underlying mathematical programs for obtaining provably optimal quantum circuit design. Let's now formulate the mathematical program. Here is an illustration of a generic quantum circuit parameterized by the number of qubits and the maximum allowable depth. Next, we introduce the native gate set. Here is the U3 gate with 3 continuous angle parameters, where we fix the first 2 angles to the value 0 and discretize the third angle, which is the lambda angle belonging to the set CalL. The reason we stick to these set of discretizations is to be consistent with the U3 gate implemented in the IBM's hardware. Next, we also introduce the other constant parameter gates, such as the Rx gate at the angle pi over 2, identity gate represented as I, and the 2 qubit C0 gate. Next, we introduce binary variables corresponding to every gate in the native gate set, which would be mapped into this circuit based on its location. For example, this particular variable, the zrn, d, is equal to be 1 in the mathematical program if and only if the gate Rx is placed on qubit n and depth d in this circuit. So this implies that introduction of these binary variables will ensure that every gate from the native gate set can be located at any possible location in the quantum circuit. Next, we present the constraints of the mathematical program. Although we present these constraints only in 2 qubits for illustration purposes, it does generalize to an n-qubit circuit in a straightforward way, which is what is indeed implemented in the package. Here, GD represents a variable matrix, which is nothing but the convex combination of every possible native gate, which could be located at a given depth on the qubits. Here, the Kronecker product is used to represent the appropriate dimensions of the single qubit gate when it is evaluated with respect to a particular depth. And this constraint, which is a linear function of the binary variables, represent the fact that only one gate can be chosen at every depth of the circuit. Next, we present the constraints which represent an important property of a quantum circuit, which is the unitary evolution. And unitary evolution is represented by the multiplicative property of these unitary gates, which is represented in the form of a constraint. Here, G0 represents the initial state at which the evolution begins, followed by the product of the variable matrices GD, which equates to the target computation or the target gate represented by T superscript G. Note that this constraint in its form is nonlinear and non-convex and is considered very hard to compute. Moreover, the constraints of this form cannot be handled as it is by the off-the-shelf solvers. In order to handle this non-convex constraint and bring it into a tractable form, we introduce the so-called recursive matrix linearizations. So the idea of this linearization is to recursively group the products of matrices and apply linearizations. For this purpose, we introduce the G-hat matrices, where the G-hat matrix at a certain depth represents the cumulative product of the unitary gates up to that certain depth. And hence the G-hat matrix is also unitary. Next, in order to linearize the nonlinear terms appearing in the products of this G-hat and the G matrix, we apply the well-known linearizations from the theory of disjunctive programming, for which the details can be found in the manuscript. Next, we introduce the objective function of the mathematical program. As we had discussed earlier, one of the key properties for improving the quality of a designed quantum circuit would be to minimize the total number of 1 and 2 qubit gates, which also serves as a proxy for the execution time of the circuit. For this purpose, the objective function is going to be a linear function in the introduced binary variables. The other objective for improving the quality of the circuit would be to minimize the 2 qubit gates, which is also the C0 gates, for which the objective function is again a linear function of the binary variables corresponding to the location of the C0 gates. Note that the objective functions presented here are again for 2 qubits, but they do generalize for n qubits. Let's now put everything together what we have discussed so far. For a given set of inputs, which is the number of qubits, maximum allowable depth for the circuit, a target gate or the computation, and a set of gates native to the quantum processor, we have modeled a mathematical program, or to be precise, a mixed integer program, which contains a set of variables, an objective function which is linear, and a set of constraints which are also linear, after all the linearizations which we discussed earlier. The output of this mixed integer program, or the MIP, is an optimal solution, which is also an exact circuit to implement the given target gate up to a global phase and machine precision. The details of the global phase is not discussed in this presentation, however, it can be found in the package. Solving any mixed integer program to global optimality is by applying divide and conquer type approach, or a branch and bound algorithm. Here is a branch and bound tree which represents this algorithm. Although this algorithm is applied in great amount of details, the prime idea of this method is to maintain a lower bound and an upper bound for the objective function, and tighten these bounds by applying cutting plane generations and primal feasibility heuristics. This branch and bound algorithm terminates with a global optimum when the obtained lower bound and best found upper bound are numerically close to each other. Decades of research and development have gone into development of technologies with solid mathematical footing in solvers such as IBM Cplex and Gurobi. We invoke these technologies to solve this problem of optimal quantum circuit design. Another interesting fact is that although solving a mixed integer program to optimality is NP hard in worst case, there has been a speedup of up to 200 billion factor times over this time period. This shows that solving a mixed integer program is not all that bad. Although MIP solvers perform very well on generic problems, their performance can be further improved by problem-specific enhancements. For example, for the problem of quantum circuit design, there is a lot of symmetry which can be broken by applying valid constraints. For commuting gates, we make sure that only one of these product pairs are allowable for the feasible circuit, so that it eliminates a lot of symmetric solutions. Similarly, we apply constraints for involutory gates, idempotent gates, and redundant gate pairs. We also apply reduced size MIPS by eliminating identical gates, which are typically obtained by angle discretizations of the U3 gate. We also apply reduced size MIP when the native gates and the target gate have only real valued entries. Further, it is well known that warm starting a mixed integer program with a feasible input circuit can also speed up the solver by having a quick upper bound for the branch and bound algorithm, which we discussed earlier. So this procedure also can be an enhancement to speed up the runtime of a MIP solver. We now present the framework for the QuantumCircuitOpt package, which we call QCOpt in short. QCOpt is an open source toolkit for optimal quantum circuit design. QCOpt is a registered package which can be downloaded from directly the Julia package manager or from this GitHub link. QCOpt is built upon the recent success of Julia programming language and Julia for mathematical programming JUMP package. The two primary tasks of QCOpt are as follows. The first task is to carefully craft and build a mixed integer program and pass it over to the abstraction layer of JUMP, which further is solved by the mixed integer programming solvers such as Cplex or Gurobi. Finally, once the MIP is solved to optimality, the solution is extracted by QCOpt from JUMP layer for further analysis of the optimal circuits. A menagerie of quantum gates are implemented in QCOpt, which serve as options for the native gate set. As expected, all the 1-qubit gates from the Clifford group and the T gates are implemented in addition to the 1-qubit gates with angle parameters. Also, numerous 2-qubit gates, including the C0 and the control versions of all the 1-qubit gates, are implemented. Here are a few examples to invoke a particular gate using the QCOpt package. Here is a sample implementation in QCOpt to decompose a controlled Z gate using U3 and C0 gates. First, we import QCOpt, JUMP, and a MIP solver package. Input a target gate which needs to be decomposed. The input parameters, including your favorite set of gates. Here we choose U31 and U32, which can be located on both the qubits and a C0 gate. And also we include the identity gate in order to minimize the depth of the circuit. Enter the Euler angle discretizations for the U3 gate. Choose an objective function, which is to minimize the depth in this case. And finally, let QCOpt build and run the optimization model. For this problem, the output of QCOpt is as follows. It first preprocesses, detects numerous non-unique gates, and applies all the symmetry-breaking constraints as we discussed earlier. And the output for this gate is, as expected, an optimal circuit with depth equal to 3. Let us now look at a few compact circuit realizations obtained using the package. Here is the computational setup we have used for different packages and solvers. In particular, we use Gurobi as the MIP solver for all our results from here on. And all the results are reproducible by executing the file in this link. We now present the efficacy of symmetry-breaking valid constraints, which were discussed as part of the MIP enhancements earlier. We considered various 2-qubit target gates. And this column represents the total number of native gates considered and the maximum allowable depth for the decomposition of the circuit. This column represents the MIP runtimes without the valid constraints, and this column with the valid constraints corresponding to breaking the symmetry of the MIPs. As it can be seen, there is a tremendous improvement in the runtimes for every gate consistently, and in particular for the Grover diffusion operator, there was a speed up of up to 180 times. For two important gates, we now present circuit decompositions, which we believe are new in the literature. Here is the magic basis gate, which is a 2-qubit gate implemented natively in trapped ion quantum computers. This gate has an interesting property in the cross-Sirac decomposition, where it can be repeatedly applied to universally decompose any 2-qubit unitary gate. Here is the matrix representation and the circuit implementation of this gate as discussed in this paper. As discussed in the previous slide, the magic basis gate in this paper was implemented using this circuit realization, which has an optimal depth of equal to 3. Based on this circuit, a theoretical result was proved where every 2-qubit quantum unitary gate in the special orthogonal group can be realized by a circuit consisting of at least 12 elementary 1-qubit gates and 2 C0 to 1 gates. However, using QCOpt, we obtain this optimal realization using the U3 gate with 3 angle parameters which are discretized and has an optimal depth equal to 2. By using this implementation, we can also improve this theoretical result in this paper by reducing this bound on the number of 1 qubit gates from 12 to 10. In these implementations of the magic basis gate, it is important to observe that the C0 gate is the reverse C0 in this case. However, a reverse C0 is itself an expensive gate which needs to be implemented using 5 additional gates while accounting for the hardware constraints. Hence, we now present the circuit for implementing the magic basis using C0 1-2 gate. For this circuit, one can simply replace the C0 2-1 using the circuit represented in the previous slide. And since the 2 adjacent Hadamard gates vanish, we can obtain this representation of an optimal depth equal to 4, while using the U3 gates with discretized angles and C0 1-2 and directly co-optimizing using the mixed integer program, we obtain an optimal depth of equal to 3, which is again better than what we obtained by just substituting in the blockwise fashion. The second gate we considered was the Grover diffusion operator. It is well known that this operator forms a key building block of the Grover's algorithm, which is used to find an element within a randomly ordered database of n elements in order of square root n operations, where each of these operations, as highlighted in this circuit, is represented by a Grover operator. And here is the simple circuit representation of the Grover operator and its equivalent matrix representation in 2 qubits. Here is a circuit implementation of the Grover diffusion operator as presented in this paper. This circuit has a depth of equal to 7. However, using QCOpt, we obtain these optimal realizations using different native gates in the set. Using the Clifford T and the C0 gates, we obtain this circuit which has a reduction of depth up to 42.8%. And using the U3 gate with discretized angles and C0, we obtain a circuit with depth just equal to 3 and leading to 57.1% reduction in the total depth of the circuit. This substantial improvement in the representation of the circuit was possible due to the implementation of the MIP models in QCOpt. We also obtained optimal realizations for larger qubit circuits. Here are the realizations for 3 and 4 qubit circuits, including the Toffoli, Fredkin, double Toffoli, and the quantum full adder gates. It is important to mention that these realizations are optimal and also they match with the ones provided in this particular paper. And the reason for this is that the method implemented in this paper is very similar to a brute force type enumeration algorithm where the solutions are enumerated until the best solution is found. And that was also partly the reason why the best runtimes obtained for the full adder gate in this paper was close to 7 hours, while in QCOpt, the runtimes were less than or equal to 7 minutes. Again, this reinforces the fact that mathematical programming based methods for optimal quantum circuit design problems are very effective, and in particular, which are implemented in this QCOpt package. I will conclude this talk with a few remarks. We proposed QuantumCircuitOpt, the first ever Julia-based software package, which implements provably optimal methods based on math programming models to compile any arbitrary unitary into a sequence of native hardware gates. QCOpt proved a few new circuit realizations for important gates such as magic basis and Grover's operator using universal gates with non-trivial angle parameters. QCOpt also proved optimality for several medium-sized circuits within a runtime of less than few minutes on a laptop. Finally, I would like to conclude and mention that we encourage the quantum computing community to explore this package and also contribute to this novel platform. Thank you. Here is the GitHub link where this package can be accessed.